Okay, so we have this and the next question. They come from kind of near the end of the chapter and the questions, problem 72. So I think in the textbook they are not assigned to any particular section, but this is kind of in the same group of questions that we've been doing at this session, addition of forces in 2D, and you may need to use Newton's second law to calculate the acceleration. So let's approach it the same way. And again, so for the magnitude and direction, technically you could use law of cosine and law of sines in order to skip to this right away. This time, let me just do it the standard way, the normal way, where you break the forces into components, and they are given in components anyway. So using law of cosine, that's actually extra work. So let me draw a free body diagram first. I have forces F1 and F2. So F1, negative X, negative Y. So that's going to be in the third quadrant. So do I have a mass? Yeah, I have a mass of the asteroid, 125 kilogram. And this force, it's somewhere in this direction, F1. And F2, positive X and then negative Y. So it will be, remove this. So it'll be somewhere like over here, F2. And normally we would say then, break forces into components. But here it's actually already broken into components because the question is giving you the components, This is minus 3.3. This is minus 5.6. This is plus 7.5. Minus 9.5. So for the components of the net force, which will, I guess, point somewhere in this direction, you just add the components. This for the x component of the net force, you do the x component of F1 plus x component of F2. For the y component, you do the y component of F1 plus the y component of F2. And I think it's simple enough that I can just do it in my head, because it's 7.5 minus 3.3 or 4.2. And then it's these two actually added together with a minus sign. So minus 5.6 plus 9.5. I think that's 15.1. 15.1. So hopefully that's correct. Then now the magnitude and direction of this net force. Now this degrees, if I had to guess, the standard angle to look for would be this angle here. This is my plus x-axis. This angle here would be kind of the standard angle to ask for. So let me calculate that. The magnitude is easy enough. The magnitude of the net force, use a quadratic formula. You got the y component, the x component, and the hypotenuse. This is your net force. That's gonna be square root of the x component squared plus the y component squared. This I think I need to do in the calculator. Let me do it here. So I got x component of 4.2 squared. Y component is minus 15.1, but negative sign will cancel out. So 15.1 squared. Square root of the whole thing. That should give me the magnitude. 15.7 Newton. And for the angle, this is the way I would approach it. So you do make use of these x and y components. And you might have seen this standard formula, one that says tangent of theta, let me use phi, is equal to, actually I think I can use tangent of theta, that'll be correct. Tangent of theta is equal to Fy, the opposite, over the adjacent, Fx. Now, if you simply do this and do the arctangent, I think you're going to get a wrong answer. Let me just do that to double check. So I'm going to do the y component of force, minus 15.1, divided by the x component of force, 4.2. And if I simply do arctan, it'll give me a negative answer. And And I don't know if the question is looking for a negative answer, because this calculation is basically giving me this angle here. You know, and you could kind of make an argument that this angle is the same angle here, just expressed differently. But if you answer minus 74.46, I think it's gonna say it's wrong. Or never mind, it says it's right. But it says that's wrong. Okay. Let me see. I didn't say. Square root of 4.2 squared. It's possible that the question has relatively tight tolerance, so it might want 15.67. The default tolerance on my open method is 0.1%. A lot of the physics questions we use 1% tolerance, but this must still be using 0.1%. I'll notify the author. It's if they'll change it to 1% tolerance. So yeah, that actually makes me wonder if accepting this angle, if it would accept the other version. So 360 minus 74.46, like that would be more of a standard answer that maybe should be graded as correct. But let's give it a try. So 285.54. Yeah, it doesn't grade it as correct. I mean, this is one of the reasons I give you practically infinite tries. Either answer could be valid, and here the question author decided to accept this and not the other version. So just give it a couple tries until you get the right one. There isn't a deep lesson here, so I think it's fine. So, if the mass of the asteroid is 125 kilograms, what acceleration does it experience in vector form? Oh, so here's the quickest way to do parts C and D. I basically take the answer to part A, divide by 125. Part A, divide by 125, that should give you the matching answers here. So I do 4.2, divide by 125, 0. So I gotta be careful here. Because it's a 0.1% tolerance. And then this is minus 15.1, so minus 0.128. That should be my component answers. Great. And then here, so the angle would just remain the same. Don't divide the angle by 125. The acceleration and the net force are in the same direction, but the magnitude will be simply this divided by 125. So let me do 15.67 divided by 125. So 0.12536. Let's hope it's within 0.1%. Yeah, I don't like 0.1% tolerance. It's there are so many different rounding things that can cause that much error. So yeah. Okay, let me get to the next question. I think it should be more or less the same question. Let me see. All right, it's this question. I guess it's not a more or less the same question. So problem 79. Yeah, because in the previous question they just gave us the components that made some of our calculations easier. Here they didn't give us the component, so so let me just approach this in a standard way without complaining too much and just chug through it. I'm gonna draw a free body diagram, which basically will be a copy of this because they did give us a free body diagram. I just wanted to label things here my own way. So I should start out with defining the axis. Oh wait, they defined the axis for us, and since we are asked to answer in these components, we should stick to the axis that they are giving us. So x and y. So what I need to do is I need to break forces into components. F1 is fine. I got 10 Newton here. Just that's it. The x and the y component of F2, I need to work it out. So we are given this angle here as 37 degrees. So I've drawn the right triangle in the process of breaking F2 into components. So what I need to do is locate this angle within the right triangle. And I got these two parallel lines. So this angle must be the same as that angle, 37 degrees. So that kind of tells me. And having written that out, I remember, my trig relationships. So ka, and here I guess I don't need to use twa, so I'll just stop at so and ka. It says what this is mnemonic for is the sine of an angle is the opposite over hypotenuse, and cosine of an angle is the adjacent over the hypotenuse in a right triangle. I write this out because here it's a little bit unusual. Your x component, it's the opposite side of the angle. So your x component will actually be f2 sine of the angle 37 degrees. That sometimes people, automatically associate x with the cosine, y with the sine. There are angle arrangements where that won't work out. So I recommend going through this right triangle exercise every single time so that you'll be right every single time. And the y component, because it's adjacent side, it'll be f2 cosine of 37 degrees. I have to do something similar with the f3. So that'll be the x component here, y component here, added together gives you the hypotenuse. This is a right triangle. And this is 37 degrees, and for the same reason this angle here should be 37 degrees, so the x component here will be f3 sine of 37 degrees. It's opposite to that angle, and this will be f3 cosine of 37 degrees. Okay, so for the net force, I think all I need to do is just add all these components. The x component, I got this x component, this x component, so it should be f2 sine 37 degrees. And let me put my sines, SIGN, into my equation. I know my f3 component is going to the left in the negative direction, so I'll say minus f3 sine of 37 degrees. For the y component of the net force, I got three forces, the two upward from F2 and F3, and one downward from F1. So I'll say minus F1 plus F2 cosine of 37 degrees plus F3 cosine of 37 degrees. Let me do this calculation in Wolfram alpha using a vector-like notation, or more precisely, I'm gonna do it as a tuple kind of calculation. So parentheses, this will be first element of the tuple. That will be F2 20 Newton times sine of 37 degrees minus F3 10 Newton times sine of 37 degrees. That's the x component. And the y component will be minus 10 Newton plus F2 20 Newton times cosine of 37 degrees plus F3 10 Newton times cosine of 37 degrees. And this should give me an answer basically in tuple form. I think that's supported. Yeah, coordinates work. Yeah, I guess kind of. If I sketch the net force F, it'll have an ending point there. Now, they're not asking us for the coordinate, the net force itself. So I would put in 6 and 14. They're asking for the acceleration. And here's the reason I put in this way. So in this format, I can just divide the whole thing by mass, 16.2 kilogram. And that'll just give me components of acceleration right here in this format. Oh, wait. Oh, because it got confused by kilogram. Let me erase the kilogram, and it'll just do the coordinates calculation. Yeah, I got x component and the y component. I can just type it in 0.371. Let me round it there. Let's see if this 1% tolerance, 0.862. Yeah, that's it. Yeah, so that's the second question. Net force, divide by mass to get the acceleration. That's it. Pretty simple.